Hello, my name is Jack Michael. This is Physics 2211, Lab 1, Constant Velocity. The main physics principle observed in this lab is an object moving with zero acceleration or at a constant velocity. This is in line with Newton's first law of motion, inertia, which states that if a body is moving at a constant speed in a straight line, it will keep moving in a straight line at a constant speed unless it is acted upon by an outside force. Because of this law, I have to assume that the object I'm observing, which is a bouncy ball, as you'll see in a minute, is experiencing zero net force over the duration of its observed movement. Because if there was a net force acting upon it, we would see an acceleration or deceleration due to loss of energy from friction. That would make the object not have a constant velocity. The model for position of the object that I observed um, matched extremely closely to the actual observation, as you can see here, with the orange dots being the model and the black line being the actual observed position. And as you can see, the two line up extremely closely. Here's the video I used to uh, get my observed data. As you can see, I roll the ball with some initial velocity from the right of the screen to the left of the screen. The clip is about 1.4 seconds, which is important for my model, and the ball moves with a constant velocity from the in the negative x direction, with right being positive and left being negative. These are all useful for my model, which is shown here. Each of these three things highlighted are things within the model which I edited. First, as I said, the time of the clip is about 1.4 seconds, so the loop lasts for that amount of time. The net force, as I said, we're observing an object in constant velocity, so no acceleration, so there is zero net force applied to the object. And the position update, I calculated how much it should update each run of the loop by observing how the distance, the displacement of the object over the 1.4 seconds, and took the displacement over the change in time, which gave me the average, or the average change in position, which I needed, which was negative 0.0252 in the x direction. This outputted this model position graph on the left, which is the position on the y-axis and time on the x, and the observed position on the right. As you can see, they are extremely similar, having extremely similar slopes. The main difference between the two graphs is the model position is extremely or perfectly straight, while the observed position has some bumps in it due to minimal error in data collection in the tracker app. But as you can see, the two are practically the same, with the every one of the X model points landing on the line of the actual observed position graph. First question, what would happen if the positive and negative X directions were interchanged? Well, that would just result in a graph that is inverted over the x-axis, as you can see here, like this. It wouldn't change anything really about the data, except it would multiply it by a scale of -1 to change it from negative x direction into the positive x direction. Finally, as I said, I assume that there is zero net force applied to the object. In reality, there is minimal loss of energy due to forces like friction. So if we want to observe true constant motion, we would have to have a constant force which is opposing the minimal force of friction throughout the duration of the ball's movement to generate a net force of 0. That's the end of my presentation. Thank you for watching.